All right, so we're going to start by learning about the periodic table some more, and then get into radioactive decay, which is the topic of the lab. So last thing I said from last class period, from Monday, is that we don't need to memorize this periodic table, but we need to familiarize yourself with it to know how to read it and to know what kind of information it tells you. So here is the best periodic table I could find. I did a lot of searching on the internet. I found ones that I thought were more visually appealing, but they didn't have the names for these elements here. So this one is pretty good. This is the one that I will give you on the exams. So you can familiarize yourself with it and be good with that. So let's just look at what is on here. First of all, this periodic table is probably not, I say probably not, it is not the ideal periodic table. There were a number of periodic tables, that is, tables of the elements that were made historically. And this one is based off of the periodic table that Mendeleev created. In fact, there is an element on the periodic table that's Mendeleevium, that's named after the person who came up with this periodic table. It's not Maryland, it's Mendeleevium. So what Mendeleev did is he took the chemicals, well, the elements, remember elements are a single type of atom, and he arranged them by chemical properties so they behave the same chemically. So you have the same kinds of reactions. And so going horizontally, what we call the groups on the periodic table were going across horizontally. Each column represents different chemical behaviors. And then if you have two elements that have the same chemical behavior, roughly speaking, he put the heavier one down below. Now, he didn't have exactly this table because he was purely basing it off of chemical reactions. But the table has been modified and improved so that it has more organization to it, but it still has that basic premise. So if you look at the right-hand column, we call those the noble gases. They're noble because they stand alone. They're also called inert. And on this table, you can actually see why they're noble. So let's look at the center, the symbol thing that tells us how to read this. So we have in the top left corner the atomic number. What does the atomic number tell you? Number of protons. If it's neutral. And this here is, so Z is the symbol for it, and it's the number of protons. The bottom center, you have the name. I don't think I need to write anything for the name. And then you have the atomic mass. The atomic mass is A. And what does the atomic mass tell you? Yes. Why the number of neutrons plus protons? Because the mass of an electron is so small that it's essentially just the sum of those two. Now, if you want to be specific, some places will use atomic mass and we will say A is an integer. And it is indeed what I just wrote. But if you actually look, you'll see that the atomic masses are not integers shown here. That's because they're actual masses in atomic mass units that vary somewhat, because the mass of a proton is not always the same and the mass of a neutron is not always the same, which is something we'll get to when we talk about radioactivity. But you have the atomic mass, the atomic number. So in any of these, and remember, you will have this on the test. It won't say Z and A, but you can find the atomic mass and the atomic number, and you'll have this key to make sure. Then we have another thing that's very important in chemistry, the valence. And the valence is telling you about how it is found in atoms. So or in atoms, in molecules. A molecule has one or more atoms bound together. And when they bind together, you have electrons that might give up another electron or share an electron. And so the valence is telling you about its number of electrons when it's bonded with something else instead of a neutral atom. And those valence electrons tells you about how it behaves chemically. So Mendeleev designed this based on how it behaves chemically. So if we look here at, for instance, the noble gases all have, well, at the top, oh, come on, reload. They have valences. That was exactly not what I wanted. Valences of 0. What that means, krypton has a valence of, and xenon has even more. Those other numbers mean that they do form some reactions. They can form some chemical, some molecules that aren't alone. The ones with just 0, that means we only find them by themselves, except for very special cases. I did research with like excimer lasers, an excited dimer, and you can make an excimer with, these. But those zeros are telling you that they don't really react. So it goes right along with them being noble gases, also known as inert. And then we have this column here. It's called the halogens. These ones here were the noble gases. The halogens, you notice, they have a valence of -1. What this means is these things like to grab another electron. They like to have one extra electron. So if you look at fluorine, how many protons are in the nucleus of a fluorine atom? 9. It says right there in the top left corner, 9. But in the top right corner, it says it has a valence of -1. That means when you find it in a molecule, it's going to have a charge of -1, which means it has one extra electron, so 2 electrons. So fluorine likes to have an extra electron. And then if you come over to oxygen, what does oxygen like to have? 2 extra electrons. Now, if you go over to nitrogen, you've got a whole bunch of numbers there. We typically say, well, nitrogen likes to have 3 extra electrons, but it also has some other options to it. And so nitrogen is a little more complicated in its chemistry than oxygen and fluorine. So those columns are based on, what it wants in terms of electrons. Fluorine and chlorine, as we'll see, they're 1 electron short of being in a stable configuration. That's why they want the extra electrons so bad. And so these fluorine is like your most reactive element. It's the one you want to stay away from the most because it really, really wants to have that extra electron. Coming over here, hydrogen has a valence of +1. Come on, come into focus. Or -1. Hydrogen, it turns out, when I was a kid at least, we had a periodic table that had hydrogen listed right here as well as right here. Because hydrogen is in a very, very unique situation. It turns out that we'll get to this later, but you can have 2 electrons in the lowest energy level for an atom. So hydrogen, a neutral hydrogen atom, should have 1 electron. If it gives up an electron, it's in a stable configuration with nothing. If it gains an electron, it's in a stable configuration with both electrons that it can have. And so hydrogen goes both ways. It can both give up its electron, or it can say, give me an electron. So that's why it has both the minus and plus, and why in this periodic table I had as a kid, it appeared at the top of the halogen column as well as at the top of the alkali metal column. So all of these, you see, they all have +1s. I know Nathan knows something that these things have in common? What do you know, Nathan, that these things have in, I should keep going because the videos that you showed me, they did stuff that was crazy. What do those have in common? Yes, they're in the same column. What did we watch on those videos with idiots doing? You don't remember? They were putting them in water, and they explode. They explode in water. Why do they all explode in water? Well, it has to do with that +1. They're all going to react very strongly with the water in a very strong exothermic reaction. And so we watched things go boom, and it was fun. Would have been more fun if we could do it ourselves, but we can't. Now, a last thing to note here, alkali metals, these things here, the red boxes. It's the first column or the first group of alkalis. This group is alkali earths. So you see alkali earths are the orange ones. Transition metals. The transition metals fill in, I don't have a yellow pin right now, fill in this middle section. And you'll notice some of the metals you're very used to are transition metals. For instance, iron, something we're all very familiar with, I think. Nickel and copper, very common. We wish this was more common. Silver, in the same column as copper, silver, and gold. Over here we have mercury, another reasonably common metal. So we have a number of these transition metals. Those are what we think of as metals. Well, kind of. There's also the category here that's a basic metal. The green ones are basic metals. Well, you're familiar with aluminum, probably familiar with tin, with lead. You do not have to say, oh, yes, of course, tin is SN. You don't have to have that memorized. Right? Don't put on your potential test questions what is the abbreviation for tin? Because you don't have to have that memorized. That would be a poor question if I tell you you don't have to have it memorized. You say, here's a question to ask on the exam. You say she needs to change her question now? I know you're joking. He said asking, and I... Okay, so we have those basic metals. And then we have a very interesting thing, the metalloids. The metalloids would be these things here. I learned to call them a different thing. I learned to call those the semiconductors. Right? Most people know silicon's a semiconductor. Germanium's a semiconductor. Not so much people know about arsenic or boron being semiconductors. And anything else of interest here? Yeah. The last thing is these elements down here in the bottom. I'm going to change colors because I just realized I've done everything in red, and that is going to make Hannah feel uncomfortable. You have a question?
So why are the two paint stickers in the main table not labeled, but no one does? There they are.
That's actually where I'm going right here. So why are they labeled and not labeled? Well, remember I said this is not the perfect table. It's not the perfect table. It turns out there is an organization to this that's a little beyond this class. But the elements, the numbers of protons goes top left is 1, top right is 2. Then you go down, you have 3, 4, 5, 6, 7, 8, 9, 10, and so on. Well, as you get to lower and lower, we call them periods as you go down the table. As you get to the lower and lower periods, you have more elements in the period. Remember I said you have just 2 electrons that go into the lowest energy shell? And so that's why you have 2 atoms in the first period. One for electron 1, one for electron 2. And then you go to the second period, and you can put electrons in the second shell now. And when you put electrons in the second shell, there's a total of 6 electrons in the second shell. Yeah, just counting to make sure I did my math right here. 6 electrons in the second shell. So in the second period, you have 2 electrons in the first shell and 6 electrons in the second shell to give you a total of 8. In theory, if you went down to the third, you would have another shell, but the energy is too high, so it doesn't come down to the fourth period. You have the next shell that you put in was the 10 transition metals there. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, 10. Actually, I should have 5 times 2 is 10. We did a quicker way to get to that number because you have 5 electrons and 5 electrons. You go down 2 more periods, and then you have the next, which is a set of, I believe that's, what is it? 18? No, I should know these numbers offhand. It's not like they're hard to come up with. 1, 2, 3, 4. Okay, so there's 15 listed here. But you have an additional 14 then that are added on. And so all of this from lanthanum 57 to, I don't know how to pronounce it, I'm going to go with lutetium 71, all of those should come after barium and before hafnium. And so that's shown down here because it would make the table super, super long if you put them in there.
Dash is like AL through or LA through LU.
Yes. All of those go right here. And then the actin, this is called the lanthanide series because it starts with lanthanum. Lanthanum. That's it, lanthanum. And this is the actinide series because it starts with actinium. But those should all be fitting in here. Now we say that our periodic table is complete now. We have a complete 118 elements. All of them have been discovered. And as is indicated on the table in the back, not all of them have been discovered in nature. Only 90 have been discovered in nature. The others are man-made. So things like Neptunium, it's man-made. Neptunium was the first man-made element, and Neptune was the first predicted and then discovered planet. So there is a time between those. Likewise, plutonium is the second man-made element and was the second predicted and then discovered. It wasn't close to what they thought they had predicted, so it doesn't fit the planets. It's lost its planethood because of not fitting, but that's why we have those names. Then we have americium. First guess, where do you suppose americium was discovered? America. Curium, that's named after Marie Curie. Berkelium, take a shot. Berkeley. Yes. Californium. Yes, because these were all discovered at Berkeley, at a lab in Berkeley, California. I think Einsteinium and fermium were as well. I'm not sure about that. Mendelevium, Nobelium, Lawrencium, it's Lawrence Livermore National Laboratory in Berkeley, California. But so the United States was pretty active in finding these. Now, if you look at the most recent ones, nihonium, where would that have been discovered?
It says like Nihon.
I would go with Nihon.
Where's that?
Nihon, oh my.
It's in Asia. India.
Nihon. The land of the rising sun, Japan. So that's, I'm sure, found in Japan. Well, maybe you've certain like what is it? Honda or Datsun, which is now Nissan, is Nippon Motors. Nippon is an alternate pronunciation for Nihon. Just something that you might be able to tie into. Okay. Flerovium, I have no idea. Muscovium. Yeah, it's got to be Moscow, Russia, right? Livermorium?
Liverpool.
Nope.
No.
It's Lawrence Livermore Laboratory in Berkeley, California. Tennessee. Pretty sure. Oganesson. I think it's back in Russia again. I'm not 100% sure. Okay, so it's interesting to me to look at these names, but those ones that we just went through are the most recently discovered elements. This year is, at least according to the American Chemical Society, the International Year of the Periodic Table. So I'm spending extra time on it because it's the year of the periodic table. Why? Because we now have a complete periodic table. Does that mean these are the only elements that you could ever have? No. We have a whole bunch of man-made ones. You could make more. It's just going to take a lot more energy.
But they can't exist in the environment, can they?
Well, they will decay instantly.
Yeah.
So exist in the environment, they're going to decay instantly. They're highly radioactive, which once again is topic of the day.
How do they find if they succeeded in making a material?
That's actually a good, solid question. Since they pretty much instantly break apart, how do you discover it? And what they do is they look for the energy associated with them then breaking apart. And so they're looking at signatures other than the standard, here's a chunk, let's study it. And so when you get to that level, you start realizing that science really is quite a faith proposition. You're believing in things not seen.
You're believing in facts or theories. But
You see evidence of something and then you're inferring what it is.
yeah.
So when we talk about, back there in the back, we have the central picture is showing a helium nucleus. A helium nucleus contains 2 protons and 2 neutrons. But scientists looking at the properties of protons and neutrons came up with the idea that protons and neutrons themselves are made up of smaller particles, made up of things called quarks, as we name them. That's a nonsense word from James Joyce's Finnegan's Wake. And no one's ever seen a quark. They infer them based on the properties that they see in the protons and neutrons. So once again, quite a faith proposition doing science. It's not as clear-cut as we tend to think. One of the things I want future teachers to understand is that while I believe in science, it doesn't mean science is right. Okay, things about the periodic table. Everything we have is made from stuff in the periodic table. So I don't have a fake hip. Good news. But if I did, they'd make it out of something like a titanium alloy. An alloy is where you mix different metals together. Titanium is the predominant metal there. Silver, I don't have any silver settings, but some people use it for placemats for TSAT as shown here. Diamonds, my wife has a diamond ring because it was her grandmother's.
Trying to get me one of those.
Trying to get you one of those?
Tell my boyfriend.
All right. What I'll tell your boyfriend is.
I told him, but he's not listening.
No. What I would tell your boyfriend, this is going a little off topic, but the whole value of the diamond is just based on propaganda. Diamond companies, and there's basically one, paid a lot of rich people to advertise, wear diamonds in movies and whatnot, and make people think diamonds are important.
I don't care if
And
it's small.
they control the production of diamonds, and they get people to believe ridiculous things. When I was in graduate school, I had a classmate, a good friend, who was working on trying to make diamond-like films. We could not make man-made diamonds at that point, and they were working on the process of trying to make diamonds. Now they can make diamonds. They can make diamonds that are perfect diamonds without defect. And you know what Zales will tell you? That those are inferior. The man-made diamonds are inferior. No, they can make it perfect, or they can put in defects to give them colors if you want, colors in your diamonds. They can do that too. They can make any diamond you want. And they can make it for cheaper than Zales sells them. Now, Zales produces them for very little, but they sell them for very high.
When you tell them, I don't care if it's small. I don't care if it's perfect. I just want it now.
It's now is the important thing. So cubic zirconium will do.
exactly, whatever, fine.
Okay, so I'm really opposed to the diamond industry because it's the classic example of monopolistic behavior on something that has a little value in that usage. I mean, it's pretty. It does have a lot of really good values in materials. Diamonds are very hard. They have very good thermal properties. They're actually very useful materials, and yet people wear them on their fingers. Okay, so let's just move on. So I talked about the groups and the periods. So here's a picture. There's the picture. Come on. Just in case you got confused on what a column was versus a row. So the periods are the rows, the groups are the columns, and notice it's sixth period subset because it fits in there. And you'll notice here, this is going with your comment, Amber, this periodic table actually shows lanthanum right here and then starts with the next one. Different periodic table. The best periodic table is a big spiral. A big spiral that has hydrogen and helium, and then keep going around circling, you get to lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, you come back to sodium, magnesium, and you just keep spiraling, you have more elements as you go down in the circle. That would be the best periodic table, in my opinion. But, how are you going to put that up? You can't put that on the wall, right? You can put it around the room maybe, but it's not very convenient. So this is the convenient one. Yeah, I have a chandelier periodic table. So names for things in the periodic table. You should know this one, this one, this one, and this one. Oh, and this one. Don't worry. Notice it says no common names for ones that we had names for on the first periodic table I showed you. And we do have the Chalagans, which I had never heard of until I read this textbook. And you'll notice that I don't think that one was on the periodic table. I don't think it was on the periodic table I showed you. Now, so you do need to know those things. I'm going to give you that periodic table that actually has them, but you know what the downside is? It's going to be in black and white. So you won't be able to cheat and say, oh, this is a noble gas because it's this color, because it'll be black and white. I know that's disappointment, but got to make sure everything's clear.
Please don't touch it yet. Wait, what do you mean?
Oh, on the test?
Yeah. On the test, you need to make sure you know the alkali metals are the first column. The alkali earths are the second column. The transition metals is this block here. And then the halogens is the next to last group. And the noble gases is the last group. It doesn't say them back there.
Oh, okay.
And you'll have a periodic table that says more than that, but it's in black and white, so you won't be able to read it because it's color coded on, right? You'll have this periodic table, but you won't be able to tell what color is what, so you can't just read it from the color codes. Was there a question there, Hosanna?
No, he was
I was knighting.
You were knighting her. Okay, we've already talked about the lanthanide and actinide series, so get past that. Now, some important things that we have otherwise in the periodic table. Which atom is larger, lithium or fluorine? What do you think? This is just an opinion question now because I haven't talked about it. Which do you think is bigger?
fluorine.
Okay, fluorine. I got a quick answer. Anyone else? Okay, we have agreement on that. Here is a table showing atomic sizes.
But weights.
More.
No.
Oh.
No.
There's not. I didn't think that. I was just. He gave me an N and I had to do
It's
it.
more basketball.
Oh, you're
It's not mass. The mass is going like this, right? So this is the most massive element on this. It doesn't go all the way down. It stops one row short. But that's the most massive element shown here. Actually, it's two rows short. But yeah, the size is how big it is. Okay, volume. Yes, volume is accurate. Notice helium, even though helium has 4 times the mass of hydrogen, it's smaller. It's smaller because you have stronger forces holding the electrons to the nucleus. And then lithium is bigger and the sizes get smaller as you go to the right. So the noble gases are smaller in size. They also get smaller as you go up. So the smallest element is helium, and the largest element on this table is rubidium. So size, the largest is lower left, the smallest is top right. So because lithium and fluorine were on the same period, then the one that's farther to the left is bigger, the one farther to the right was smaller. If they're in the same group, then it's going to be the one that is farther up is smaller, the one that's farther down is bigger. One of the things that scientists used to identify chemicals in weird ways, one of them was the taste test, which to me seems awfully bad because some chemicals are definitely dangerous to taste. Another one is smelling. Well, I don't know if you've smelled a lot of chemicals, but some of those things are pretty bad on your nose when you smell them, right? They can be bad.
Like egg salad.
It's true.
If you donate plasma, you taste copper when it goes back into you.
If I exercise too hard, I taste copper because of the bleeding in my gums.
And say, like, if you want to taste copper, it's just like that. Go donate plasma.
Okay, so another thing they would do is they would put them in flames and see different colors. So remember last class period I had the lamp out here, you wore the sweet glasses and you could see the different colors? Well, you can do that by burning elements. And so here's some examples. Strontium, those are the colors that you see if you put it in a flame. And so they look at it in the flame, and of course, they probably, back when they were doing this, were seeing something like this picture. But now we can analyze it like this and say, aha, there is the signature set of energy levels for strontium. Or for potassium, right? There's potassium in the flame, it's blue, and there's all of the colors that make up that blue. Barium, what do you do with a dead chemist? You bury him, that's right.
That's a knee slapper.
It is. That's the kind of jokes the chemists tell. I was going to tell some that I learned from my son. He called me like at 10 p.m. one night to tell me a chemistry joke.
That's true friendship right there.
Yeah. It was something like, hey, did you hear about the sodium? Nah. Good stuff, huh? All right. So moving on. Copper has a pretty green color, and here's the spectra for that. So we have these unique colors. We already saw that for hydrogen, helium gases. These are metals, you put them in a flame, and you can see those unique colors. Where they come from is from the energy levels of the electrons. When you give off light, the light is given off because an electron falls from a higher energy state to a lower energy state. And in so doing, it gives off light with energy equal to that energy difference. The energy for a particle of light is a constant, Planck's constant, times the frequency of the light. And so when we look at these spectra, these spectral lines, wow, it's not worked for me. There we go. If we look at these spectral lines, if we determine what the frequency of each one is, then that tells us the energy difference between where the electron fell from and where it fell to. Because the energy difference is H. Really? It's when I go to the top of the screen, in case I have figured out what causes it. So the energy difference between the electrons' energy levels is HF. So looking at these, we can start to decipher some information about the energy levels of electrons in atoms. right here.
What is the H?
Okay, H is equal to 6.626 times 10 to the minus 34. That's a 3. Joules times seconds. That's Planck's constant. It's a constant number. And F is frequency. Yes, ma'am.
How much longer is lecture?
How much longer is lecture? Probably around 20, 30 minutes.
Okay, because I still have a question.
Because what?
I still have a question. Digital test question.
Oh, yeah, plenty of time. Plenty of time. You have a question, Amber? All right. How can the hydrogen atom has one electron, right? That electron is naturally just going to be in its lowest energy state. So how can we have a whole bunch of lines with this simple element with just one electron? It's what? The electron can vibrate at a variety of frequencies.
No.
Not it. No, there's no harm. You're guessing here. You're supposed to be guessing. Any other ideas?
D.
Okay, D. Many standing electron waves can fit in the shell of the hydrogen atom.
Not either.
All right, well, then I'm going to go A.
You're right. It has just one electron. It's naturally in the lowest energy state. But you can do things to give that electron energy and make it go to higher states. Because it has a bunch of different energy levels the electrons can have. It's just naturally the lowest one. So, like if you have room temperature hydrogen atoms, you can have lots of electrons that have actually, because of collisions between the atoms, jumped up to the next energy level. And in fact, if you raise the temperature to 10,000 kelvins, then you're going to have most of your electrons are in the second energy level instead of in the lowest energy level, just because of collisions. If you do something like shine bright light on it, if the light has the right energy, the electron can absorb the light and go up to another energy state. And then it can fall back down to any lower energy state. And so that's how you can get the different colors, even though there's only one electron. Because that electron can be raised to a higher state and then fall down to any state below it. Shell model. I don't know how that got there. The shell model is saying that we have different energy shells for the electrons. I've already been talking about this, right? I said the electrons have different energy levels.
Yeah.
We call those shells. This picture is highly deceiving. It's highly deceiving because it makes it look like you have spherical shells that the electrons are on. It's a model. It's not a reality. Remember, a model is a framework for making it easy to think about. It doesn't have to be true. And in this case, it's not true. The electrons are not on spherical shells. We don't know where they are, but we know that the symmetry isn't even spherical unless it's an s orbital. All the other orbitals don't have spherical symmetry. So this model is good for thought, but it's not reality. But one thing to note, 2 electrons go in the first. Then we have 8, then 8, then 18, then 18, then 32, then 32. Those correspond with the number of elements on each of the periods in the periodic table. You have 2 in the first period, 8 in the second, 8 in the third, and so on. Now, the funny thing is, the first 2 of these 8 are in what we call the 2s. And the next 6 are in the 2p. They're actually different subshells, s and p. So you have 2 and then 6 to give you 8. This one here should go to 18. You have a 3s, a 3p, and a 3d. But the 3d is higher energy, and so it didn't actually occur to here. So this here is just to fill you in on why we have the number of elements in each of the periods. Now, how is that going to play out for us? Very soon, we're going to find ourselves doing electron dot pictures for bonding. And so here are models for the shells showing the filling. So, not pi filling, sadly. So hydrogen has one electron. So we have a circle with one ring, the first shell, and one dot on it, one electron in that first shell. Get over here to helium. Helium has one ring with two dots on it. It's completely filled. Only two dots go in the first one. Then we go down to the second period. Now we have two rings. The inner ring in each one is exactly the same. So we never will write those, okay? If we're in the second period, we're only going to show the second shell, not the first shell. And then we had one here for lithium, two for beryllium, 3 for boron, 4 for carbon. And then when we got to 5, they start doubling up. So we go around and we show one at each top, left, bottom, right, until we get to 5, and then we have 2, 1, 1, 2, 1, 1, and question, Amber.
Like circle lines and it's spread out.
Um,
Like they have one and one.
The reason is actually for a good reason. When we show electron bonding, we're going to show, okay, if I have one here and I bring two atoms together, then they can form a covalent bond. That's the way we're going to show it. If I have two here, then it can't have it anymore because it can only have two there. So that's the reason we have it that way. Yeah.
So the next line would have 4 big circles.
Yeah. And so this is going to come back when we talk about bonding. Radioactivity, the topic of the day. Yay. What is radioactivity? Well, it's the topic of the lab today. What is radioactivity?
Radioactivity.
The amount of decay and all that.
Sorry, I thought saying it would help me, but it didn't.
Okay. Well, here's my demonstration for radioactivity.
It's waves.
This pin is representing the nucleus of an atom. And that pin is pretty stable there, right? Until I do something, I don't want to push this table too hard. But if I pound the table, you can easily see, or I'm just going to tap it a little. If I tap it a little, it falls over. And it fell down to a more stable configuration. It has lower potential energy now, right? That's what's going on with radioactivity. The nucleus is in a stable configuration, but with a little bit of jarring, it can be knocked to a more stable configuration.
And it transfers that energy to the atoms around it.
It's going to give off energy in some fashion. In this case, it gave off energy. How did you know it gave off energy?
The sound.
You could hear it, right? That sound was energy coming away from it. Now, the energy that's coming off of atoms when they undergo radioactive decay, the nucleus is a much bigger energy situation than this is. And so it's giving off, well, I say much bigger, it's actually smaller in numbers, but more significant. It's giving off very highly energetic things. So coming off, you're going to have a number of things, and we're going to start, well, actually, we start with what holds it together, and then we'll get to that. So I'm going to get to that very soon. So radioactivity results from a radioactive decay, from the nucleus going from one stable configuration to another more stable configuration. And radioactivity has existed longer than the human race. Okay, well, fine. Radioactivity, the key here is that it's not a man-made problem. It's something that is natural. And it occurs with unstable nucleus.
So you'd say it's a problem?
In some cases, yes. Like if you were, well, I'm sure you've read about something that sticks in my mind. A Chinese farmer found this little hut and it had these gold-looking balls in there. And so he took one, put it in his pocket, and went home. And then he got really sick and died within a week.
Yeah, like sometimes you can't have kids if you've been close to something that's radioactive because it kills.
Yeah, because it was the thing he picked up was highly radioactive. It was something that had been developed for nuclear research of some sort, and then left a band in there. You didn't know what it was. As far as you knew, it was a shiny piece of metal. Right? Who gets scared of a shiny piece of metal? Okay, I'm sorry. Most of the radiation we encounter is very natural. For instance, there is radiation going through your body right now. There is radiation coming from the sun, coming from stars. From the sun, it would be solar radiation. From the stars, it's cosmic radiation. Here I just combined both and called it cosmic rays. Very high energy particles flying through you. Most of the time, it does you no harm. Every now and then it does. You know, someday I'm probably going to get skin cancer because of all the time I spent out in the sun as a child, right? And my ears would just be crusty. It was terrible sunburns. That's from radiation. Now, when we talk about radiation, just like when I talk about chemicals, some people get all bent out of shape about, oh, chemicals are dangerous. Some chemicals are dangerous. We talk about radiation, some radiation is dangerous. Is the radiation from my cell phone dangerous?
Yes.
Wow, we got pretty good consensus there.
It is, because if you keep holding it up to your phone a lot, like if you use your phone a lot,
You have a hard time sleeping at night because of it.
like
That's a fact.
Because it distracts you?
No, because the light from your phone messes up your brain.
Okay, light from your phone. Okay, go on.
What? I'm so serious. This is a
Yes,
serious
but it's not the microwave radiation.
As long as you know that you need to be careful so you can sleep better.
But Hannah, go on.
go on that way.
You were talking about the danger.
I don't want to get it wrong, so I'm not right.
That's okay.
No,
We're in a class where we
I
learn.
don't like getting something wrong.
This is not the master class for everyone who's got their doctorate in physics.
Are you sure about that? Because my grades say
You
otherwise.
learn better from making mistakes.
Just saying.
No,
Mistakes are-
there is a lot of conjecture that the microwave radiation, the radiation that's coming out of your phone, which is the type of radiation, it's not the kind we're talking about here, is dangerous. We know there's radiation coming out. That's the intent. The intent is that we communicate with this radiation. The problem is that going to harm us? We know we can cook food with microwaves, right?
You're not supposed to stand in front of it.
Yeah, and you're not supposed to put your poodle in the microwave.
Your poodle?
Your poodle?
You guys haven't seen those? Yeah.
You
Did you put a dog in my microwave?
No. But there are stories about people who want to dry their dog, and so they put it in the microwave.
Or warm up their baby. What?
Well, their baby, not the milk, but the baby. Oh, that's sad.
Makes me sad what you do to your cat too.
It makes me sad too. Yeah. Just for the record, if you happen to watch Fun Things to Do in a Microwave, and you read the one about you
Putting
can
your
charge your
phone in
microwave
it,
in
don't
5
do it.
or your phone in 5 seconds in the microwave. Yeah, don't do it, okay?
Don't put foil in the microwave either.
Yeah. Okay, so the microwaves, we know we can cook stuff with it. The microwaves, remember that equation E equals HF? Yes, you do. Good. What was that question?
I have a thing.
Thing?
It's really funny. My
I'm
friend-
sure it's on topic, so go ahead.
It is. My friend put popcorn in the microwave for too long that it set it on fire and we had to leave school.
Nice. Good. When I was at PUC,
Patient, not my friend.
we had the standard problem. Somebody wanted to put something in the microwave for 10 minutes, instead they put it in for 10 hours. And this occurred during the student talent show. And so, of course, the smoke starts billowing from the fire that started inside the microwave. And so the fire department gets called. We get up there. First of all, students were throwing glass bottles at the fire trucks. What kind of idiots? We were a little upset. We get in there and we're clearing out the dorm, and we had girls hiding in their closets because they didn't want to have to leave. There's a fire in the dorm, but they didn't want to have to leave. At one of our sister colleges, boy, this has been more than a decade ago, I think it was 2 girls who actually died in the fire because they were hiding in their room. And by the time they realized, no, this is really a fire, it was too late. Right, so that's bad to do, okay?
Yeah.
And in the end, it was just the microwave. Yeah, take care of that, and then we got to leave, and it was all good.
Why are they throwing glass bottles at you?
I don't know.
Drunk or something. People
No, they weren't drunk. I can't answer. I don't have any good reason. But back to this.
Radiation.
That equation E equals HF. The energy in the microwaves is too low to break bonds, to break chemical bonds. And so we consider it safe because it's too low of energy to break chemical bonds. The reason we cook food is because we don't break bonds, but we make molecules vibrate. So we transfer energy, make them vibrate. They're moving faster. That means that their temperature is higher. And so that's how we cook with it. So the concern is, okay, we're probably not going to directly break bond, cause cancer, but we could start cooking. And so they've done experiments like having people with a phone strapped to their head all day, some of them turned on, some of them turned off. And they did find that people with phones turned on had slightly higher blood flow on the side of their head with the phone, which tells you there's some kind of thing going on, right? Now, the difference in blood pressure was less than the difference between sitting and standing up. So it wasn't a major difference, but it's still nobody's sure. There have been lots of scientific studies, and there's nothing definitive saying it's unsafe or safe. There's some that go both ways. You have a question, Hannah?
Is the microwave thing still like applicable if you microwave it at a higher voltage or whatever it's called? Like when you can like change how high?
Oh, okay, power setting.
Yeah.
The power setting, at least with the microwaves I have owned, which is not an exhaustive set, it's just setting the duty cycle. What percentage of the time is it on? What percentage of the time is it off?
Okay.
And so, yeah,
It's still okay.
Okay, so the radiation that we worry about here from nuclear stuff, you can't get off radiation like what we've been talking about. But you also get charged particles. And cosmic rays are what's responsible for the carbon-14 in the atmosphere. Carbon-14 dating occurs because of those cosmic rays making nitrogen turn into carbon. And then we can measure things like how old a fossil is based on that. When an atom undergoes radioactive decay, what does it do? So think back to my example with the pen. What does it do? Okay, it becomes more stable. And it's going to have to give off energy, right? Because the difference in energy from where it started to where it ended, just like when this goes from here to here, give off energy. That energy could come in the form of something leaving the nucleus that has mass. If something leaves the nucleus that has mass, it's going to become maybe, it could have a different element completely. That is, you could have the number of protons changed because of something left. Or you could have that it's the same element, but you have a different energy state. So you have actually, it may or may not turn into a completely different element is the correct answer. It could do either one. So elements can change. Radioactive decay can change an element. The carbon-14 that I talked about, you start with nitrogen. I think it's plus a neutron. This is the way we write. That star means it's unstable. That's the reaction that creates carbon-14, if my memory is correct. You have a nitrogen atom. The air is 79% nitrogen molecules, so there's lots of them. It absorbs a neutron. Neutrons have no protons, hence a 0 down here. But they have a total of one thing in the nucleus, the neutron, so it's 0, 1. Proton is a 1, 1. And it creates an unstable nitrogen 15 that then breaks apart. It's radioactive and decays into the carbon 14. That carbon 14 is itself unstable. And so the carbon 14 on its own will spontaneously decay into a, I believe it's a neutron. I think that's what it does, but I could be wrong. I'm pretty certain about this one, not as certain about this one. Actually, yeah, I think this bottom one is wrong. I don't remember the decay, so I'll just leave it. So radioactive decay will change an element from one thing to another. Now, wouldn't it be lovely if we could find something that was plentiful that would decay into gold? So for instance, you look at the periodic table, mercury has one more proton. If we could find a way to knock a proton out of mercury, we could turn mercury into gold. What did we call people who tried to do that, who devoted their lives to it? Crazy people. Alchemists. When I was a child, I too thought that it must be possible. I watched the movie The $1 Million Duck, and I couldn't figure out how exactly applesauce plus the duck's metabolism, maybe there was a way. It was wrong. But it is possible to make gold, like if we take platinum and we bombard it, we might be able to make a little bit of gold, but it's going to take a lot of energy and not be worth it, especially because you're going from something more valuable to something less valuable, going from platinum to gold. So radioactivity. When radioactivity was first discovered, the discovery story is actually kind of interesting. Oh man, I can't remember his name. I think it's like Becquerel, but I could be wrong. A guy was studying uranium salts and taking pictures. And so after work one day, he took his film and he wrapped his film up carefully in aluminum foil so it wouldn't get any light in. And then he put it next to his uranium rocks and he went home. The next day he came to work and he took pictures. His pictures were all cloudy. Like, what? So he developed some film that he hadn't used and the film was all cloudy. It had been perfectly fine the day before. Well, did we just have a test? Yeah, we had a test. I gave it back to Lindsay today. And we have the scientific method. The first step is observe something interesting. He observed something interesting. His film was fine yesterday. Today it's not. And so what's the second step? Create a hypothesis that does three things. Okay. Explains why your observation occurred was one thing I heard. Based on scientific ideas, makes testable predictions. And so he said, well, there must have been something coming out of that uranium rock that was exposing my film. Because I had the rock next to the film. And so if that's the case, then I should be able to take film that I know is good, bring it here with uranium and maybe take a picture of uranium rock maybe or something just by putting them next to each other. And so he did experiments to verify, sure enough, there was something coming from that uranium rock that was exposing his film. And so then we get a whole bunch of people involved studying this, like, what in the world's going on? Because scientists are very curious people. That's why they went into science. And so one of the things that was studied was what happens if you put these charged particles through a magnetic field. Or these charged particles. What happens when you put this radiation through a magnetic field? Now, if there's no charge, nothing should happen. But if it's a positive charge, it should bend one direction. If it's a negative charge, it should bend the other direction. And so they tested and they found that there were three fundamental types of radiation that they observed. One was a positive charge that bent slowly. One was a negative charge that bent quickly. And one was neutral. And by studying those, they named them based on how easy they were to stop. So alpha particles are very easy to stop. And from their measurements, they found that they had a positive charge. So positive. There we go, positive electrical charge. And they also were very massive compared to the others. Now the betas, the betas had a negative electric charge, and they were harder to stop. And they had a much lower mass. And then the gammas, the ones that were the most penetrating, so the gammas are hard to stop. They have no electric charge. And so we have these three fundamental different types of things. More careful. Nice job. I've got the S but not the E. There. No, there. Close enough. More careful observation identified what these things exactly were. And it turns out that the beta particle is an electron. And the alpha particle is a helium nucleus. No electrons, but 2 protons and 2 neutrons bound tightly together. And the gamma, well, I'm just going to put EM wave here. Electromagnetic wave. The same thing as light. So these are very different things, but they all carry energy. If you have an alpha particle come out, you've dropped by 2 protons in the nucleus. So for instance, uranium decays by an alpha decay. So if you look back there at the table, if uranium loses 2 protons, what's it going to become? I didn't hear what you said, sorry. Well, just give me the first 2 letters. TH, thorium. So uranium, it does give off of an alpha particle and becomes thorium. Now, that thorium might give off a beta particle. Here's the confusing thing. What do you have in the nucleus of an atom?
Protons and neutrons.
Protons and neutrons. The beta particle is an electron. This is radiation coming from the nucleus. How do you have an electron come from a region that has no electrons? It's kind of a poser. And the answer is actually more complicated. When I was in high school, I was like, oh, this is really simple. And a neutron must just be a proton plus an electron. But it's not. But effectively, that's the way it works. You have particle physics interactions where a neutron is destroyed and replaced by a proton plus an electron. And so the electron is created in the nucleus and then emitted. So it wasn't there, but when the decay occurs, the electron's created and away it goes. And there's another thing as well. There's the electron antineutrino that has to come with it. So that's what is actually happening with a beta decay. And this electron here is called the beta particle. There are more radioactive products than just these 3. There's also a beta plus decay, which is where you have a positron. Just like an electron, but with a positive charge. You what?
Sounds like a transformer.
Like a transformer, huh? And so the beta, this here is a beta minus decay. The beta plus decay goes like this. And that tells you right away, wait, must have been wrong about that idea about the neutron being a proton plus an electron, because you can't have a proton as a neutron plus an electron, but a neutron, yeah, it doesn't work out. It's something more complicated. So just a brief rundown of the radioactive particles that are common. The alpha particle is 2 protons, 2 neutrons, the helium nucleus. Those are tightly bound together. It's a very stable nucleus. That's why it's the goal of making a fusion reactor, because it's a very stable nucleus. Because the alpha particle is very massive compared to the other ones, it will lose energy quickly. It's easy to stop. So I can protect myself from alpha radiation like this. This is good enough. It'll protect me from alpha radiation. So my skin is also a good protector from alpha radiation. My skin may absorb it, I may get skin cancer, but it's going to protect the rest of my body. On the other hand, if I were to eat something that's giving off alpha radiation, then it's going to be absorbed by something in my body that might be a little more damaging to me. So eating radioactive material is a much bigger concern than having it around, especially for alpha emitters. Causes significant damage to the surface of material due to its great energy. Picks up electrons and becomes harmless helium when it's traveling through the air for a far enough distance, and is deflected by the magnetic fields. Beta particles are electrons, or like I said, you have a beta plus that's an anti-electron, a positron. Has a small mass, has an electric charge, loses energy at a slower rate because of its smaller mass. And so that's going to take like several sheets of tinfoil to protect me, not just a little thin piece of paper. It's just an ordinary electron. The only thing that makes it dangerous because it's going really fast. Then the gamma rays, same thing as light, just high energy light. This here is actually a concern because if that gamma radiation hits you, it has enough energy to break bonds. And so if you break bonds, like you say, you break a bond in your DNA, it may not repair correctly. And if it doesn't repair correctly, and by the way, the alpha and beta particles can also do this. If the broken bond doesn't repair correctly, you're most likely going to have cell death, which is no big deal, unless a lot of it happens. Why did that guy in China die? Because he had too many cells dying, his body couldn't keep up with the dying cells. We call that radiation sickness. Or there is a really unlikely, but very major concern. It could be that that broken bond repairs incorrectly. And it makes something that is viable, something that's not going to die, but that reproduces rapidly.
So that's cancer.
And that's cancer. So cancer is like the least likely thing to occur from radiation, but we worry about it a lot because it can occur. Why does all of this occur? We have learned about two forces. In physics, we learned about two forces. We learned about gravitational force and the electric force, electromagnetic force. But there are two more forces. There are a total of four fundamental forces. We learned about half of them in physics. The other half only are observed at very short distances, such as in the nucleus of an atom. And these other two forces are called the strong and weak nuclear force. Our textbook only talks about the strong nuclear force, so I'm just going to talk about it. So the strong nuclear force is an attractive force that is holding things in the nucleus together. Now with mass, all mass was attracted. With the nuclear force, it's the same thing. All things that interact via the strong nuclear force are attracted. But it's a different set of things. The things that have a charge for the strong nuclear force include protons and neutrons that don't have electrons. So protons and neutrons will have this very strong, it's called the strong nuclear force because it's very strong. So they'll have this strong force attracting them together if and only if they're super close together. So the strong nuclear force holds the nucleus together, but they have to be really close before it can start to exert its force. Whereas the electromagnetic force is a much longer range force. So if I have two protons, if I want to make hydrogen fusion, Nathan, if I want to make hydrogen fusion, I have these two protons, as I get them closer, that electromagnetic force is going to repel. So they come toward each other and then they push each other apart. I'm going to have to make them have a lot of energy to get them close enough for that strong nuclear force to become strong. But if I get them that strong, then they'll hold together because of that strong nuclear force. So this graph here is showing if I have two protons right next to each other, they'll have a very strong, attractive, strong nuclear force. A pretty strong, repulsive electromagnetic force, but not as big as this. So they're held together because the net force is pulling them together. But if I separate them, the strong nuclear force quickly drops to zero. whereas the electromagnetic force stays pretty strong. And so when they're a bit apart, they're definitely going to be pushed apart. That's what holds the nucleus together. That's the thing we're dealing with when we talk about nuclear forces. Just skipping over that. So here's an example of what's going on in a helium nucleus. Helium nucleus has 2 protons, the 2 red things, 2 neutrons, the gray things. The forces are attractive between protons and protons, as well as neutrons and neutrons, as well as protons and neutrons. Always attractive for the strong nuclear force. So we have forces pulling all of them together, but then we also have a repulsive force due to the electric force between the 2 protons. If we have more force holding things together than pushing them apart, it's going to stay together. So this helium forms a stable nucleus because of that. If I put more positive charge in here, it's actually not going to be stable anymore. Even though another proton is going to be attracted to the proton, the repulsion is pushed out. So how do we make an atom with 3 protons in the nucleus if adding another proton is going to make it fly apart? We have to add another neutron. The neutron will give it more attractive force and allows you to separate those negative charges so that you weaken the repulsive force. So as you get bigger and bigger atoms, you have to have more and more neutrons to keep the nucleus stable. So, well, that's what we have here. Now, this really is the topic of today's lab. Half-lives. Radioactive decay. Things naturally, if you have an unstable nucleus, it will naturally just decay. Some are very likely to decay. Every second there might be a 50% chance it's going to decay. Others are unlikely to decay. It might be that it's going to take 1,000,000 years before it's 50% likely to decay. And so things that have a short time before they're going to decay, we say those are highly radioactive. Things that have a long time, we say, well, that's not so radioactive. That's a lower radioactivity. So half-life, which I didn't define on that one, the half-life is the time for a given element that I expect half of all of my elements to decay. So if I have, let's say, carbon-14 in like 5,300 years, ballpark, I expect half of my carbon-14 atoms to decay. And so that's its half-life. That's the time when I expect half to decay. What would happen if I waited 2 half-lives? That is a logical conclusion, but not the right one, it turns out. For every half-life, half of them should decay. So if I start with 1,000, 1 half-life later, how much should I have left? 500. If I start with 500, 1 half-life later, I should have 250. So if I start with 1,000 and I go 2 half-lives, how much should I have remaining? 250 or 1/4. Both correct answers. So the reason radioactive decay works this way is because it's a probability. Every second there's a certain probability of decay. And so it's like rolling a die, which is why that's what we're doing for lab today, is rolling dice. Just to make sure we understand terminology, because we have the right words in our lab guide. This is called a die. 2 of these are then called dice, just to make sure we know the singular versus the plural. So you don't roll a dice, you roll a die. Second, that would be the number 1, right?
Yeah.
That we call this dot here a pip. So that's 1 pip. What is on the opposite side of 1? 6. So you have 6 pips there.
Pips?
Yes, pips.
Alright.
And so the opposite sides of a die always add up to 7, right? We assume these are fair dice. I assume I put that one back in the one I took it out of too. So with these dice, if they are fair dice, that means for each die, when I throw the die, I have a 1 in 6 chance of a 1, a 1 in 6 chance of a 2, etc. So on average, how many times do I have to roll the die before I will get a 1? Yeah, because it's a 1 in 6 chance, you say, well, probably if I roll it 6 times, I'll get 1. That's not the way it actually works, because the first time you roll it, there's a 1 in 6 chance of a 1. The second time you roll it, there's a 1 in 6 chance, which means that there was a 5/6 chance that you didn't get the first time, a 5/6 chance you didn't get the second time. By the time I've done it 6 times, the likelihood that I have not gotten a 1 is 5/6 raised to the 6th power, which is not 1. So we're going to do statistics with these dice. Just a few more things on half-life, and then we'll get started. So we've already done this math. If we started with 1 kilogram after 1 half-life, we should have half as much. 2 half-lives, 1/4 as much. That was what Jessica said. After 3 half-lives, 1/8 as much. After 10 half-lives, how much should you have left? It's 1/2 raised to the 10th, which is like 1/1024. So it's 1/2 raised to the n. Remains after n half-lives. So what is a half-life? It's the time when you expect half of it will have decayed. And here's an example of transmutation. Here's the production of carbon-14 as I showed you earlier. You have a neutron that comes in, is absorbed by the nitrogen-14. It creates the unstable nitrogen-15 that's shown right here. Well, it didn't show it right here because it was the unstable nitrogen-15 that broke into the carbon-14 and the nitrogen. That's a transmutation because you change from one type of atom to another type of atom. Another one here, a uranium decay that I talked about in class as well, uranium-238 decaying via alpha decay to become thorium-234. Notice the number of things in the nucleus, 234 plus 4 is equal to 238. Those numbers in the superscripts, the atomic masses, have to be the same because we can't create or destroy mass fundamentally. Now my last slide or two will say, yes, we can, but it's a small amount. Likewise, the numbers in the bottom, 92 is equal to 90 plus 2. The charge can't be created or destroyed is what that's telling us. So we can balance these equations. We have to have the same number of protons on the left side as on the right side, and we have to have the same number of neutrons on the left side as we have on the right side. This here is talking about the transmutation with decays. Let's see, that's not what I was looking for. Let's get to, I'm not even going to talk about, well, I will. Radiometric dating. This is actually something that's important to many creationists, such as me. Radiometric dating is a method that is used to measure the age of things. And we, as Christians, very often talk about carbon-14 dating. Carbon-14 exists in our atmosphere because of the cosmic radiation transmuting nitrogen-14, the common nitrogen, into carbon-14, an uncommon radioactive form of carbon. Then that carbon-14 is breathed in by animals. It's breathed in, if you will, by plants as they undergo their photosynthesis. And then we all eat plants. Even carnivores, when you think about it, are eating plants because they ate an animal that ate a plant. That's really the source of nutrition. So basically, everything that eats is going to have carbon-14 in it to match the carbon-14 in the atmosphere. But when you die, you stop eating. And so that means you stop bringing in carbon-14. And so then the carbon-14 that's in your body is going to decay over time. And so the goal of carbon-14 dating is let's measure how much carbon-14 is in something and compare it to how much it had when it died. And this brings up the first obvious question. How do you know how much it had when it died? Well, what we do is we take the ratio of the normal carbon, carbon-12, to carbon-14, the radioactive carbon. And so if the ratio of carbon-14 to carbon-12 is what it is in the atmosphere, then we say, oh, it just died. But if the ratio has dropped, then we say, because it's dropped, it's been this many half-lives, and so it's this old. But then that had its own assumption. The assumption that the amount of carbon-14 to carbon-12, that ratio in the atmosphere was the same when it died as it is now. That's actually a really silly assumption. It's one that scientists don't believe, okay? Some people say carbon-14 dating is flawed because we weren't back there and we don't know what the ratio was. But what scientists have done and have done very carefully is they have taken things that they can date by a different method. Something like you find it in an archaeological dig. You know, there was this battle at this time, this stuff was buried there. That's how old this is. They measure what the ratio is now and they extrapolate back to get what the ratio in the atmosphere was at that time. So they've actually carefully calibrated what the ratios were in the past history. But then there's the real drawback with carbon-14 dating. Carbon-14, there's not much of it in the atmosphere. Because there's not much of it in the atmosphere, after a while, you just don't have any measurable carbon-14 left. So carbon-14 dating, at its very best, might be able to measure 100,000 years in the past. Most people say between 50,000 to 100,000 years. Anything beyond that, carbon-14 dating simply cannot date. It's too old for it to date. So if we're talking creation versus evolution, creation times are less than 100,000 years. Carbon-14 dating is highly relevant. But evolutionary time scale, 100,000 years is a blink of an eye. And so for evolutionist standpoint, carbon-14 dating is simply not reasonable. It's not useful because we're talking about things that are older than that. But then I have to bring up something that I find really disconcerting. In recent years, they have found carbon-14 in dinosaur bones. Dinosaurs that are supposed to be like 60 million years ago they died. How much carbon-14 should remain after 60 million years? The half-life for carbon-14 you see up there, 5,760 years. Okay, so I had the number wrong. 5,760 years. Well, if you're 60 million years, then you've gone 10,000 half-lives. How much remains after 10,000 half-lives? Well, 1/2 raised to the 10,000 is a number that's really close to zero. And there already starts with very little carbon-14. So there really should be no detectable carbon-14 in any dinosaur bone. And yet they found it. Furthermore, something within the last decade, they have found tissues, things like proteins, in 60 million year old dinosaurs. Well, proteins, as we best understand them, decay, right? You all know that if you leave your food out on the counter, it's going to rot. That's because the proteins are decaying. And after about 70,000 years, you should have nothing left of the protein. It should be completely destroyed. And yet they find proteins in dinosaurs that are supposed to be millions of years old. How do they get those millions of years old? They get them by using these other radiometric methods down here with half-lives that are much bigger. 4.47 BY, that means billion years. Well, uranium-238, that's about the age of the Earth as we understand by science. So about half of the uranium-238 that the Earth started with, it still has. Uranium-235 has a half-life of 710 million years. Rubidium-87, 48.8 billion years. Okay, that's a really long time. Potassium-argon, 1.248 billion years. It's a very useful one for evolutionary time scales. That's how they get the ages for those dinosaurs. And so one might wonder what we're missing, because we have radiometric dating that says it's billion or millions of years old, and then we have some carbon-14 which says it couldn't be that old, and we have these proteins that say it couldn't be that old. So there's still something we don't understand going on here. Nuclear fission. If we want nuclear power right now, it's nuclear fission, breaking things like uranium into two smaller pieces. You have a chain reaction that occurs in a fission power plant. Notice you have one neutron coming in. That one neutron splits the atom, but we had 3 neutrons coming out. So if I can make this happen, every time I split an atom, I can now potentially make 3 more atoms split, which means the rate at which I'm going to split atoms is going to increase exponentially. Each time you split the atom, you're going to a more stable configuration. You're releasing energy. If you release energy at an exponential rate, we call that a bomb. So that's how nuclear bomb works. Nuclear power plants, they want to absorb. So you just action you cause, you have one more that occurs. So it keeps going at a constant rate. It's kind of a very careful balance. If the rate increases, it blows up, or it melts down, as we like to say. If the rate decreases, then it cools off and it's no longer going to produce power. I'm a big proponent myself. I'm a fan of nuclear power. I think it's a good way to get rid of all of this radioactive material that's naturally occurring in the earth. Uranium is created when stars die, and the earth has a certain amount of uranium from stars that died before the earth was formed. And, there's energy there. Okay, last thing is where the energy comes from. We're not talking about bombs, okay? I'm not talking about bombs. In the early 1900s, Albert Einstein came with this equation that says E equals mc squared. What this equation says is that mass is just a form of energy. So you look at me and you say, Richard's got a lot of mass. It would be just as accurate to say Richard has a lot of energy, because Einstein says energy is just proportional to mass. So it's a true statement. Now, my sister posted something about when things are, let's see, I gotta think about this straight. I'm going to mess it up, so I'm not going to say it. The punchline was, I'm not fat, I'm hot. So mass is just a form of energy. Now, when we look at the mass of an atom, I told you that the mass of a proton neutron changes a little bit. And it depends on how strongly the nucleus is held together. So we make graphs. Here's a graph of the mass per nucleon. The nucleon is a thing in the nucleus. So if you have 2 things in the nucleus, their mass is here. If you have 4 things in the nucleus, the mass is here. And if you get down to iron, the mass per nucleon is the lowest value. What that means is you have decreased the mass by converting it into energy in a different sort. Energy is holding it together. So that iron is the most strongly bound nucleus. It's going to be the hardest to break iron apart. Anything else, if you can force 2 nuclei together and they go to a bigger mass that's still less than iron, it's going to release energy. And the mass of the protons and neutrons is going to drop. So, just a quick question. In which element is the mass of a proton the smallest? Iron. Iron. The one with the smallest mass per nucleon there is iron. So a proton has the smallest mass in iron, which means that iron is bound together the strongest. And so if I can mash things together to get closer to iron, it's going to release energy. Or if I take things larger than iron, I split them, I can release energy. Now, if you look at the way this is shaped, going from uranium to iron is not nearly as much energy as going from, let's say, hydrogen to iron. So you have the biggest energy available by going from hydrogen toward iron. That's the fusion process, making things merge together. So one of the grand searches in physics is trying to find a way to control nuclear fusion so we can make nuclear fusion power plants, because there's a lot more energy available there. All right, it is now time for us to do the lab. So let's look at the specific lab. Like I said, this lab is very short.
Doesn't look short.
It is short. So we have here some discussion about radioactivity. I've just gone over some discussion on radioactivity, so I'm not going to spend any time on that, other than to note that different elements have very different half-lives. Polonium-214. Polonium is named after Poland, which is where Marie Curie was from. Very, very short half-life. Whereas carbon-14, 5,730 years, uranium-238, 4.5 billion years. So we're going to simulate different radioactive decays. So you're going to start with, and I'm going to have you work in 4 groups. One group will only have 1 person in it. So you guys can all fight to be the one working alone. It doesn't really change the time involved. Okay, Amber will work alone. So you're going to start with 25 dice. I have 4 beakers with 25 dice. And the first time through, you're going to roll those dice, and you're going to count how many ones there were. So in this roll here, I had 1, 2, 3, 4 ones. So in your table, you should have at the top of the table that you started with 25 here. And now I had 4 ones, so I'm going to put 4 here for the removed, which leaves me with 21. Now those 4 removed, I just set aside. I put the rest of them, by the way, if I had taken out the 2s, I would have taken out about 8 that time. Statistics don't mean a lot with a small number. 25 is enough that it will work out. But if we did this with 25,000, it would work much better. It's just, this wouldn't be a short lab in that case. So now I'm going to take my remaining 21. I roll them again. And once again, I count how many ones and remove them. So this time I had 3 ones. So I put my 3 here, and I'm left with 18. And you keep doing that until you get to finally a 0 in this column. Once you've done that, then we'll go to the next page, and you're going to graph them. Try to use 3 different colors if you can, if you have that at your disposal. So you're always going to start here at 25, because before your first roll, you had 25. In this case, after the first roll, I had, it was 22, right? Is that right? No, 21. And then after the second roll, 18. I looked over there so I could double check my count. And you mark them on there. I'm just going to put what it could be for my next rolls. Okay, it's got to be on the intersections. Okay, so that's just made up data for the rest. Then you make a smooth line through those points. You're not connecting the dots. If you connect the dots, you'll lose points, okay? A smooth line means, and I'm going to change colors here because I can. You start here and you come like this. Okay, the last part didn't go so well. Like that. Sound effects are not necessary.
I think we need to embed a button into our worksheet.
Anyway, so you draw that smooth curve, and then make sure you label so it's clear to the grader, otherwise known as Nathan. That was removing the ones. Then you do it a second time, but this time it's going to go a lot faster because you're removing the 3s and the 5s. If you remove the 1s, what's the odds for each one coming up a 1? Blank out a blank.
Wait, can you do it again?
Can you say the question again?
If I'm removing the 1s, what are the odds when I roll a die that it will come up a 1?
1 out of 6.
1 out of 6. Now the second time you're going to remove the 3s and 5s. What are the odds that it's a 3 or a 5? 2 out of 6. So you've doubled the odds that it's going to be removed, right? For the last one, so you're going to go through and do the same thing, but this time you're removing the 3s and 5s. For the last one, you remove all of the evens.
So that's why you want us to have 3 different colors, because we're graphing each different.
Yes. So you're making all 3 graphs on the same set, on the same graph here. So you now have 3 lines. Did you have a question, Jessica?
When I remove the 3s and the 5s, what if I roll 1? So
The 1 stay.
they stay the second time?
Yeah. Yeah. So that it's a completely different set experiment. So you're going to go through with 3 different odds. One that's a 1 in 6 chance, one that's a 3 chance, and one that's a 1 in 2 chance. And then you have some questions to answer based on your 3 experiments. That's it. Any questions?